Hello everyone. In this lecture we will explore the magnetic vector potential by means of a simple scenario in which we will consider the current as well as the geometry of the scenario to find out first the magnetic vector potential and then use that magnetic vector potential subsequently to find out what is the corresponding magnetic field. So coming to the magnetic vector potential, so we have the knowledge that the divergence of the magnetic field is always 0, and also there is this identity in vector calculus that the divergence of any curl is 0. So divergence of B is 0 and divergence of curl of any vector is always 0. So which means B can be written as the curl of some another vector field, and that other vector field is what we call as the magnetic vector potential, and we generally represent this by A, the vector A. So now there is a requirement. We'll find out what is the requirement on A, but here we are only confining ourselves to magnetostatics. So the requirement of A can be obtained by considering the Ampere's law, and the Ampere's law, what does it say? It says that the curl of the magnetic field is equal to mu naught J. So now we can just replace this B with curl of A, and this gives us curl of A is equal to mu naught J. Now this can be expanded. This is a second derivative. This is a type of second derivative. We are applying the curl twice, and expansion of this is given as gradient divergence of A minus Laplacian of A, which is equal to mu naught J. So here we will consider what is called as a gauge transformation. So there is a lecture which I have earlier delivered. It's on my channel. It's called the gauge transformation. So over there you'll if you watch that, you'll know exactly what exactly is a gauge transformation. But just to put it simply, a gauge transformation is any transform that leaves the fields invariant. That is, we can transform the potentials. We can move from one set of potentials to another set of potentials, and we are allowed to do that as long as the fields they remain invariant. Okay, so we can have a kind of a gauge transformation which will ensure that the divergence of the magnetic vector potential is 0. So if the divergence becomes 0, then this first term becomes 0, and as a result this expression becomes very simple. This gives us that the Laplacian of the magnetic vector potential is equal to minus mu naught J. This minus comes from this side here. Okay, so now this is a Laplacian of a vector. Now A can be written in terms of its components Ax, Ay, Az, and J can also be written in terms of its components Jx, Jy, and Jz. So essentially what we can do is we can write down this is actually a collection of 3 equations, one for each component. So component wise we can write this down, the equation, as 3 equations. So one equation will be for the x component, one equation for the y component, and one equation for the z component. And these 3 equations, if you look at them, they look very similar to the Poissons equations for magnetostatics. So what is the Poissons equation in magnetostatics? The Poissons equation is that the Laplacian of the scalar potential is equal to minus rho by epsilon naught. We had obtained this expression also in a very similar way. How did we obtain this expression? We obtained it this way. We considered the Gauss law, which is divergence of E is equal to rho by epsilon naught, and then like over here we had, instead of the Gauss law, we had the Ampere's law, and then here we replace this electric field with the fact that the electric field can be written as the negative gradient. The electric field can be written as the negative gradient of the scalar electric potential, a negative gradient rho by epsilon naught. So this minus and we take it on this side, so this del dot del is going to give us the Laplacian. So you get the Laplacian. So it's the 2 derivations are pretty similar to each other. So this is the Poissons equation for electrostatics, and we know what is the general solution, the most general solution for the Poissons equation. The most general solution is basically this. Now of course even I have written the solution like this, but this is basically the definition of the electrostatic potential. So it is Kq by R. So K is 1 by 4 pi epsilon naught, and q, so we have to of course integrate over the entire distribution. Q is rho times d tau. In the most general case, the charge is distributed over a volume, and r is the separation distance. So this, here we have it. So this is a Poisson's equation, and its most general solution is given by this. So if you look at each of these three equations, they are mathematically they are similar to this equation, because you can see it. So here we have a second derivative, the Laplacian of a scalar, because ax, even though a is a vector, but a is made up of three scalars, right? Ax, ay, and az. These are three components, right? We can consider them to be like scalars. So ax, of course, I mean, if you look at the definition of a vector, I mean, we cannot consider them as scalars, but just the fact that they don't have any these three components, they don't have any individually, they don't have any associated directions. The directions become associated when we consider the unit vectors also. So this ax, ay, az, they are individually, they are like your phi. Okay, so this is like the scalar field. So individually these are scalar fields. We bring them together, we get a vector field. So we have the Laplacian of a field is equal to minus some constant. The constant here is 1 by epsilon naught times density. You can look here, Laplacian of a field is equal to minus some constant times density. J is the density. So mathematically each of these are similar to this. So the solutions for each of this should also be similar to this. So we can actually figure out what kind of solution we will have. So something like this. So let's say I want to find out the solution of this one. Okay, the first one. So I want to find out what is ax. So what will ax be? So just look at this expression, we just need to translate it. So 1 by 4 pi epsilon naught, instead of 1 by 4 pi epsilon naught, we will write mu naught by 4 pi, and then we will have to integrate, of course, over the entire volume. And then we have rho d tau, rho r prime d tau. So instead of rho, we will have to replace this with the corresponding this current density, which is jx at position r prime d tau prime, and in the denominator will be the same separation vector, which is modulus r minus r prime, and so on. Okay, and so on for the other ones also. So the corresponding solutions of the above, for ax will be this, for ay it will be this, and for az it will be this. So now we can combine these vector potentials. Okay, we can combine each of these three vector potentials, and this gives us combining these three, because they are all components, they are giving us the components of the vector potentials. So we can just combine them. So this into x cap plus this into y cap plus this into z cap, that is going to give us the vector A. And on the other side we have mu naught by 4 pi, I could take it common. Then this integral times x cap plus this integral times y cap plus this integral times z cap. You could just write that down. Then I could just integrate, have a common integral, and then we have x cap into jx plus y cap into jy plus z cap into jz times dz divided by modulus r minus r prime. That this components, when you combine them, that is going to simply give us the vector the current density. Okay, the volume current density. So this gives us a general expression for the magnetic vector potential, which we can use it in any scenario, and you can see here is very similar to the general solution for a scalar potential. Okay, so this is a vector potential, this is a scalar potential. Okay, very similar, because the components, they satisfy and they satisfy what are known as Poisson's equations, which are similar to the Poisson's equation for electrostatics. But then we need to always keep in mind that this is applicable only under this gauge transformation that we had mentioned, a gauge transformation in which the divergence of A is 0. So we are assuming that the divergence of A is 0. That means physically it means that the magnetic vector potential, it does not diverge out from a point. It could circulate from some point, but it will definitely not diverge out. Okay, so with that assumption, okay, we get this as a general solution. Okay, so now let's look at a problem. The problem is we will try to find out the vector potential and magnetic induction due to a circular current loop. So let's say I have a situation like this. Okay, so I have a filamentary circular loop like this, and this filamentary circular loop has got a radius of A. Okay, and it carries some current I, and it lies in the xy plane. Okay, we want to find out what is the magnetic field P at any point. Okay, so here it is more convenient if we consider the spherical polar coordinates. So we consider P to be the field point. P is a field point, the point where we are observing the field. Okay, or P is also called as the observation point. So now where do we place P? Should we place it in the xz plane or in the yz plane, or where should we place it? Ideally speaking, we should be placing P at any arbitrary point, but then we realize that in this problem, because you see the current is just going to circulate around this, so whether I look at the current, okay, whether I look at this loop from the xz plane or from the yz plane or from any other plane, the situation is going to look exactly the same, because it's a steady current. So there is a azimuthal symmetry here. You could go around like this on any plane. Okay, the situation is going to look like same. So we'll choose a plane which is going to simplify the problem. So we choose P to be lying on the xz plane, and as you will see, choosing P in this way, it reduces the number of coordinates which are variable. Okay, so it gives us some constant coordinates, so they become constant, so we don't have to worry about that. Okay, so this is how we go about doing this. So then our vectors, the position vectors, as usual, this is the R. Okay, I'm just mentioning the magnitude here. So from the origin till the field point, that is the position vector R, and from the origin till we have of course we have a current element here. Okay, so the current element IDR, so that's a current element. So this current element has got a position vector R prime, and the separation vector is R minus R prime. Now what are the coordinates of this point? The coordinates of this point is r, theta and phi is equal to 0. Okay, the coordinates of this point, that is point P. Okay, because remember here we are using primed and unprimed coordinates. So if I want to refer to this P, I need to use r, theta and phi. Okay, so this will have this r is the first coordinate, then theta is this angle that this position vector of that position vector r makes with the z axis, and phi is the azimuthal angle, and because we have chosen P to be lying in the xz plane, and azimuthal angle is always measured with respect to the x axis, so it is lying on the xz plane, so phi will be 0. So these are the coordinates. In a similar way, we can find out the coordinates of this, but here the coordinates will not be r, theta and phi. The coordinates will be r prime, theta prime, phi prime. Why? Because this is a source point, right? The current element is a source point, and we are using prime coordinates. So we have r prime. What is r prime? R prime is the radial distance. And what is the radial distance of this current element? The radial distance is equal to the radius of the wire. The radius of the wire is a. Okay. Then what about theta prime? What is theta? Theta is the angle that the position vector makes with the z axis. So here the position vector is in the xy plane. So with respect to the z axis, it makes an angle of 90 degrees. So theta prime will be equal to pi by 2. And finally we have this phi prime coordinate, which is basically the azimuthal coordinate. Okay, so these are the coordinates of the field point and the current element. Okay, so with this now we can move forward. Okay, so now moving forward, we can make a very important substitution. The substitution is, we can say that this j d tau prime is equal to IDR. Okay, the general expression for the vector potential is this, as we saw some time back, and over here there is a j d tau, but in this problem there is no j, there is only an I, right? This is a linear current I, there is no volume current j, but we know that we can actually substitute j into d tau, we can replace this with I into dr. So j d tau prime can be replaced with I dr prime. Okay, so dr prime, we are using prime because this is the source. Okay, so this phi prime is, this is the azimuthal angle. Okay, so here r prime is equal to a, as we saw, and this current element I dr, it subtends an angle d theta d phi prime at the origin. Okay, so we make this substitution in the expression for the vector potential. So this gives us the vector potential at point P to be equal to this. So what are the changes that we have made? So mu naught by 4 pi as it is. the integral, it was a volume integral. So now the volume integral has turned into a integral over a circular loop, and j d tau prime becomes I d r prime, okay, modulus r minus r prime, okay. So this I is also a constant, so because I is a constant I could just take it outside. So we have mu naught I by 4 pi, the closed loop integral of dr prime by modulus r minus r prime. So let's call this equation number 1. So now we would like to, we can only proceed if we can somehow we can replace this dr prime and r minus r prime, because we need a convenient integration variable. And here if you look at it, the most convenient integration variable is this phi prime, because if you want to integrate over this entire loop, all I need to do is just integrate over phi prime from 0 to 2 pi. So when you integrate phi prime from 0 to 2 pi, that is going to take care of the entire loop. So next step that we would like to do is we'd like to convert everything. We'd like to somehow bring in the integration variable phi prime. So for that we this dr prime we want to write this in terms of d phi prime, and r minus r prime also we want to bring in phi prime, okay. So let's try the first thing. So we look at this same diagram from the top view, okay. So here we are just looking at it from a viewing angle, okay. But let's look at the same distribution from the top, that is the current loop lying in the xy plane. So then the current from if you look at it from the top, the current loop is going to look like a circle. So looking at it from the top, this is how it's going to look like, okay. So we will have a current loop which will be like a circle. So we are just considering the current element, which is dr prime, that is the length element, which is dr prime. And as we saw over here in this diagram, this dr prime, it subtends an angle d phi prime at the origin. So dr prime subtends an angle d phi prime, and phi prime, this is the azimuthal angle. So here it is, of course it's heavily exaggerated. D phi prime cannot be so big, okay. So it's just to for the sake of our visualization. So if this angle is phi prime, using the geometry of this, if this is phi prime, then we can show that this angle is also phi prime, okay, and this distance is a, okay. So now we have this modulus of dr prime, which is nothing but this length, this is the arc length, that is equal to radius times the angle. The radius is a and the angle is d phi prime. So a into d phi prime, that is going to give us this length, okay. So that is your dr prime. So therefore what is dr? The vector dr prime, because we are not interested in a magnitude, we are interested in the vector dr prime. So what is that equal to? So that is simply going to be equal to the magnitude times the unit vector. So magnitude times the unit vector. So how do you get the unit vector? That's very easy. So all you need to do is the unit vector is going to be, you can see here, the x component, this is the x component, because the x-axis, the positive x-axis is going downwards. So the x component will be this way, and if you look at it, x component is nothing but the sine phi prime component. So the sine phi prime is going to give us the x component, and the x component is going in the negative x direction. So we'll have a minus x cap into sine phi prime. And what about the y component? This is the positive y axis. The y component is along the positive y axis. So and this component is the cos phi component. So this is going to be the unit vector, okay, the unit vector along this dr prime. So this unit vector, which is this, times the magnitude, which is this. So this gives us dr prime is equal to a d phi prime times minus x cap sine phi prime plus y in y cap into cos phi prime. So we got the expression for dr prime in equation number 1 as we wanted. We wanted this in terms of phi prime. So we got it in terms of phi prime, okay. Next thing that we need to do is we need to work out what is this separation vector, okay, the magnitude of the separation vector or the separation distance. So we can do it this way. Consider this. So I'm just simplifying the diagram over here. I just got rid of all the other things. So I'm just simplifying this. You see, if you want to find out the separation vector, we can do that by finding out what is the angle between the separation vectors. So here it is not, it may not be apparent here. So but if you consider the separation, this is the separation vector. So remember this, we have the current element over here from point P. So this is the separation vector, and this is the vector r, and this is the vector r prime. We would like to know what is this angle, okay. So let's say this angle, we call it as gamma, okay. So gamma is the angle between r and r prime. So we can now find out what is the vector. So we use a very basic result from your vector analysis. That result is, suppose I have a vector, let's say a vector A, and then I have another vector which is vector b. So we have this is vector a minus b, right? So this is going to be vector a minus b. So if I want to find out, and let's say the angle between these two vectors is, let's say, theta. So if I want to find out the magnitude of a minus b, so what will this be equal to? So we know from the vector analysis the magnitude of a minus b will be square of the magnitude of a plus square of the magnitude of b minus 2 into magnitude of a into magnitude of b into cos of the angle between them. Okay, so we can do it over here also. Okay, so we are having two vectors r and r prime. I want to find out what is the angle between them is, let's say, gamma. I want to find out what is this distance. So you can see here, if you correlate with this, I could just consider, instead of a, we could just consider this to be vector r, instead of b, this we could consider this as r prime. So this is nothing but a minus b is nothing but r minus r prime, and accordingly, and this theta is nothing but the gamma, the angle between the two. So you can just accordingly make the substitutions over here, and gives us, this gives us, of course we are going to use a directional cosine. So this gives us the separation distance. The separation distance between the current element is the magnitude of the sum of the squares of the magnitudes. So a square plus r square, then there is a minus 2 into a into r into cos of gamma, and the whole thing will be, of course I forgot here, the whole thing is under the root, so to the power 1 by 2. Okay, so now this cos gamma is what we have to find out, but we can do that very easily using directional cosines. So using directional cosines, we can find out that the cos gamma is equal to sin theta into cos phi. Just for the sake of clarity, what is theta? Theta is this angle. Okay, so this angle is theta, and what is phi? Phi is this angle. So phi prime is this angle. So using theta and phi prime, we can find out what is this gamma. Okay, the other angle, this is going to be 90 degrees. So you can use directional cosines to find out that cos gamma is equal to sin theta cos phi prime. Okay, so now we can use this cos gamma over here, and this gives us this separation vector to be a square plus r square minus twice ar sin theta cos phi to the power 1 by 2. Okay, so we got what we wanted here in equation number 1. So dr prime we got, and r modulus r minus r prime, this is also what we have got. Okay, so now before we actually go ahead and substitute these two, we will just see, examine the scenario, examine this situation, the geometry of the scenario, and we'd like to simplify some of these things. Okay, first thing that we notice is we are integrating about the x and y components only, and this gives the z component to be 0. How? Because you see the integration, we are integrating over dr prime, and where does dr prime exist? Dr prime exists in the xy plane. So it means dr prime will only have dx prime and dy prime. It does not have a dz prime component. So because it does not have a dz prime component, this integral, when we integrate over the whole loop, it will have only x and y components. So only ax and ay will be there. So az is going to be 0. Okay, so a, the vector potential a, it was supposed to have three components, ax, ay and az, but we have ruled out that az. So az is 0. We can simplify this even further. The azimuthal integration is symmetric about this phi prime equal to 0. Azimuthal integration is symmetric about phi prime 0, and as a result we will have these two results also. Ax will be 0, and only ay is going to remain. So we can see how from this diagram. If you, this again is a top level view, it's a top level view of the same current loop. So let's take a current element over here. Okay, let's take a small current element over here. This current element this is your dr prime, and this dr prime, we can break this down into two components. One is a dy prime and one is a dx prime. Corresponding to this, on the other side, let's take another current element. Okay, so similarly we have a current element here. If you look at it, this dy prime, so this is the dy prime and this is the dx prime. You can see here the dx prime here is along the negative x direction, the dx prime here is along the positive x direction. So this, when you add up these two contributions, these two will cancel out. Okay, this dx prime, they will be negatives of each other. Okay, so they will cancel out. but this dy, they are in the dy prime, they are in the same direction, so they will not cancel out. Similarly, you look at on the other side. Okay, so here we have again the x component, the dx prime component, it is along the negative x direction, here it is along the positive x direction, so these two will cancel out. But dy prime, so we have this to be along the negative y direction and this also along the negative y direction, so these two are in the same direction, so they will not cancel out. So now there could be a question here. The question is, how about these two, this y component and this y component, why don't they cancel out? The reason is, if you see the expression, as you will see as we proceed, we will find that there is a cos phi prime, there is a cos phi prime component which is going to come here. The cos phi prime is going to come. So because we are the only ay is going to remain, ax is going to become 0, so there is a cos phi prime which is going to come. And if you look at the, if you recall the graph of cos is positive in the first quadrant, negative in the second and third quadrant, and again positive in the fourth quadrant, the cos graph, right? So this is how a cos graph looks like. Okay, I'm just drawing this roughly. So this is how a cos graph looks like. So this is the full cycle. So this is the first quadrant, this is the second quadrant, this is the third quadrant, and the fourth quadrant. First quadrant cos is positive, second and third it is negative, fourth quadrant it is again positive. So here this is the first quadrant because you are starting from 0 to 2 pi. So this is the first quadrant. Okay, this is the first quadrant, this is the second quadrant, this is the third quadrant, and this is the fourth quadrant. So second and third quadrant, what will happen is this is going to be, both of them will be anyway negative. Okay, so they will so both this cos, this is going to give us a negative value, and overall, because this is pointing in the negative y direction, and the negative sign of cos phi prime which is going to appear, okay, the negative sign of cos phi prime, that is going to make these two again point in this direction. So as a result, this is not going to cancel out. Okay, when I go over this loop, the ay is not going to cancel out, only the ax is going to cancel out. Okay, so az is 0, ax is 0, so this leaves us with one component of the vector potential, which is ay. So we can say that the entire vector potential A can be written simply as ay into y cap. Okay, so let's now move further. So we have A, the vector potential A is this. So we tried to find out this and this separately. So dr prime we found out to be this, and modulus r minus r prime is this. And then we also had some kind of a simplification, that is ax is 0 and az is 0, so which leaves behind only ay. So this equation number 1 we now substitute. Okay, in equation number 1 we replace this dr prime, we replace with this, and modulus r minus r prime we replace with this in the denominator. So this is what we get. Okay, so so I have just taken this a outside because a is a constant, so it just comes outside. So the integration is from 0 to 2 pi, and this entire thing, this is what is left. Okay, so now this how does it relate to the phi component, phi r cap and theta cap component? How does it relate to it? Okay, we can see that from here. Remember the spherical polar coordinates. Okay, the spherical polar coordinates, because we are when we integrate this, what is going to be left behind is the phi component, because we are integrating over d phi prime. So what will be left behind is phi component, r component, and theta component, or in this case this x, y, and z components. X and z is 0, only y component is going to remain. Now if you recall, your spherical polar coordinates, the unit vectors, they will change from position to position. So this is the field position that we have considered. In this field position, this is the theta cap component. Okay, this is the theta cap unit vector. R cap will be radially outwards, and phi cap will be in this direction. Okay, and you can see here this phi cap and y cap, they are exactly the same. So what is the direction of y cap? This is the direction of y cap. So we can see here phi cap and y cap, they are parallel to each other. Okay, and because phi cap and y cap is parallel to each other, that means the y component of A is the same as the phi component of A. Okay, and y component is the only component, so the entire component is contained over here. Okay, so it means A, if I take modulus of A, that is nothing but A phi. So which means this AR, the radial component of A and the polar component of A, both of them will vanish. Okay, so that's a insight that we get from this consideration. So now we will try to simplify this integral further. Okay, so first thing that we need to do is, we are interested, what are we interested in? We are only interested in the a phi component. And what is the a phi component? That is the ay component, because we know that the ax component will go to 0. So which is the ax component? This is the ax component which contains that sine phi. So we might as well just get rid of that sine phi, because that is going to anyway go to 0. So what is going to leave out? You can actually verify it for yourself also. So what is going to be left behind is the cos phi component. So mu naught I a by 4 pi integration from 0 to 2 pi cos phi prime d phi prime divided by this entire thing, which is going to be, which was your ay, and now we know that this is also equal to a phi. So this is your a phi, okay, which will depend only on r and theta. So this is equation number 2. So here we would like to simplify this a little bit more. So what we do is take the quantity in the denominator. So it is a square plus r square minus twice a r sine theta cos phi to the power, there is to the power 1 by 2, but you take it up, it becomes to the power minus 1 by 2. So then what I do is, I take this a square plus r square, okay, because there is here it's in the denominator, so it becomes under root a square plus r square. So I take a square plus r square, if I take it outside, so when I take it outside, it becomes 1 by under root a square plus r square, and this entire thing has to be divided by a square plus r square. And this quantity a square plus r square, this is going to just give me 1 here. So when I take 1 by root over a square plus r square common outside, so what is left behind is 1 here. In place of this, we'll get a 1 minus, then twice ar, this entire thing has to be divided by a square plus r square. So twice ar by a square plus r square into sine theta cos phi prime, which is to the power minus half. So we can use a binomial approximation here. Okay, so you can use a binomial. If you look at the scales of all these quantities, this quantity in the second term, okay, this quantity in the second term, this is going to be, it is going to be less than 1. Okay, this is going to turn out to be less than 1. You can verify for yourself. This is going to turn out to be less than 1. So we can apply the binomial approximation here. So this quantity is approximately equal to 1 outside, 1 by under root a square plus r square is going to remain as it is. Then minus 1 by 2, just multiply with this one. So minus and minus will become plus, and this 1 by 2 will cancel out this 2 here. So we have ar divided by a square plus r square into sine theta cos phi. Okay, so this is the approximation of this quantity in the denominator. So this entire quantity in the denominator can be replaced with this. So equation number 2, we put this back in equation number 2. So this gives us in equation number 2, that is a phi, this a phi is approximately equal to mu naught I a by 4 pi, and this 1 by root over a square plus r square is going to come outside, and what is left behind in the integral is, because there is already a cos phi prime, this cos phi prime will get multiplied with 1 here, so we'll get a cos phi prime plus a r by a square plus r square sine theta cos phi prime, is there is already a cos phi prime here, and this multiplies with this, so it will give us a cos square phi prime into d phi prime. Okay, so when we insert this, this is what we get, and we can just now open this up as two integrals. So I have just combined all these other terms. So here we have mu naught I a. Okay, I think some of these terms, yeah, okay. So we take the sine theta, we can take it outside. So a r sine theta by a square plus r square, because the integration is only with respect to phi prime. So mu naught I a divided by 4 pi into a square plus r square to the power 1 by 2. So this is outside, and then we have these two integrals, and these two integrals are very easy. We already know that, because integral of cos over one closed loop is 0, and integral of cos square over one entire loop is going to be equal to pi. So this is going to be 0, this is pi, so this integral is going to vanish, and this integral is just going to give us a pi here, and that pi will cancel out with this. Okay, so we have this one. Okay, so this is the we get everything together. So mu naught I a, okay, and there is a here, mu naught I, so there's a here and there's a here, so we'll get a square, then r, okay, there's a r here, sine theta, okay, so we have sine theta, and in the denominator we have 4 into pi. Of course that pi and whatever the pi that we get here, that pi will get cancelled. A square plus r square to the power 3 by 2. So that's your a phi. Once we know a phi, of course a r and a theta is going to be anyway going to be 0. So this gives us the field to be, you could either write it in terms of the y as a y component, or you could write it as a phi component. Both of them will look exactly the same. So this gives us the vector potential in this scenario, the scenario that we had considered, that current loop lying in the xy plane. This is the vector potential. So now what's the next step? The next step is we would like to find out what is the magnetic field, right? We know the vector potential, we know the components of the vector potential. So now we can go ahead and we can find out the magnetic field. And how to find out the magnetic field? Very simple. Magnetic field is nothing but the curl of the vector potential, right? So we just need to find out what is the curl of this, curl of A. But then what is the curl? In spherical polar coordinates, this is how the curl looks like. Curl of A, this is how it is going to be. And you could refer to Griffiths for this expression that I have given here. It's mentioned over here, the reference is mentioned here. So I just use this expression and I replace this with the corresponding components. Okay, so this is the, in SPC, this is how you find out the curl of A. So we have A r, A phi and A theta, A r, A theta and A phi. A r and A theta is anyway 0. Okay, so what is going to be left behind is only A phi. So we just find out each of these components. So this component, the first one, this is going to be the BR component, the radial component of magnetic field. Okay, so let me just write this down here. This entire thing, this is going to be the radial component. So this is BR. Then this entire component, this is going to be the polar component of B. So this is B theta. And this entire thing, this is going to be the azimuthal component of B. So this is going to be B phi. So we will now go ahead and we'll find out each and every component separately. So therefore BR, first we find out BR. BR is this expression. So now the first thing immediately that we notice is, remember, AR and A theta is 0. So AR, A theta being 0, this is going to become immediately 0 because it contains A theta. There is a phi here, this will not be 0. Okay, this will remain as it is, but this is going to become 0. Then we have 1 by r, then dou by dou theta, then sine theta into A phi. So I have just taken this A phi from here and multiplied with sine theta. So there is already a sine theta here. When you multiply this with another sine theta, it becomes sine square theta. So this is what we get. And then we will proceed and we will differentiate this. So we can use, we are differentiating with respect to theta here. So we'll go ahead, we can use the chain rule to differentiate this. Everything else is a constant, so everything else will remain the same. So mu naught I a square r by 4 into a square plus r square to the power 3 by 2. So this will remain as it is. Differentiation of sine theta will give us 2 sine theta, and then using chain rule, differentiation of sine square will give us 2 sine theta, and then using chain rule differentiate sine again, that is going to give us a cos theta here. So let's see if there's certain things that we can cancel out. Okay, yes, there are certain things that we can cancel out. This r will cancel out this r, then this sine theta will cancel out this sine theta, and yeah, this 2 will cancel out this 4 and give us a 2 here. Okay, and nothing else. So this is going to give us BR to be like this. Okay, so once you have found out the radial component of the magnetic field, then we can find out what are the other components, the polar and the azimuthal component. Next we find out the polar component of the magnetic field. Okay, so now again in the polar component, AR and A phi, A and A theta is 0. So here we see there is a AR. So this immediately we know is going to be 0. So the only component that's going to remain is going to be this. Okay, so this is what we have. So minus 1 by r, dou by dou r, this minus comes from here, dou by dou r, r into A phi, dou by dou r of r into A phi. Multiply this with r, so we'll get an r square in the numerator. We'll get an r square, so that's why we have the r square over here. So this entire thing I have to differentiate with respect to r. Okay, so how do we do that? I could just take all the constants outside. So mu naught I a square sine theta by 4. There is already an r outside. Okay, by 4, and what is left behind is r square into a square plus r square to the power minus 3 by 2. So this I can use the product rule. Okay, I could use the product rule to differentiate this very easily. So when we use the product rule, we have to differentiate it one by one. So we'll have two terms. In the first term, r square will be differentiated, and this second term is going to be a spectator, and in the second time when you differentiate it, so we are going to, the second term is going to be differentiated, and this r square, okay, is going to be a spectator. So we have this r square lying over here, and then this comes because of the chain rule, because we have to differentiate inside also. The inside there is a r square, so that gives us a twice r. So we have these quantities, so some of these things will get cancelled out. Like for instance, we have an r outside and both the terms contain r as well as r here, so these will get cancelled out, and in this term this 2 and this 2 will get cancelled out, and I don't think anything else will get cancelled out. Then we will get this quantity. So we have this. So now what have we done here is, I have taken a square plus r square to the power minus 5 by 2. I have taken common outside. So when I do that, this is going to become simply a square plus r square, and here in the denominator we have a square plus r square to the power 5 by 2. Yes, everything is same. So we have this. So we have 2a square plus, open this up, 2a square plus 2r square minus 3r square, plus 2r square minus 3r square is going to give us a minus r square. So this gives us this quantity. Okay, so this is the polar component of the magnetic field. Now last one, the azimuthal component, which is going to be extremely straightforward, because both a theta and ar, both of them are 0. Both a theta and ar are 0. So this is 0 and this is 0. So as a result, the azimuthal component of the magnetic field is going to be 0. Okay, so there is no b phi component. So we got br, we got b theta, and we got b phi, which is 0. So putting all of these together, this gives us the magnetic field to be having only the r component and the theta component. So this brings me to the end of this lecture. Thank you.